CTR has so far conducted offline tech seminars focusing on general technical topics. However, from now on, we aim to hold both an online and offline seminars that focus on specific themes and share more detailed information on those subjects. This way, we can provide you with more in-depth technical insights on the areas you're most interested in. The first topic is boson separation. As you may know, if a boson fails or becomes separated, it can cause serious issues for the vehicle. That's why the automotive industry classified it as a safety part. Through this presentation, I hope your technical concerns regarding boson separation will be addressed. This is what I'm going to talk about this topic. First, let's take a quick look at what the boson is. Next, what happens if the boson separates? And what types of joint separation are there? What is the root cause of joint separation? Finally, I'd like to address the preliminary signs of joint separation. This picture is showing that the steering and suspension system of a vehicle. The red highlighted parts on the picture are 5 types of joint that CTR is supplying for steering and suspension of cars. They are control arm boson, inner tie rod, outer tie rod, a stabilizer link, and cross-axis boson. The products listed here all have different shapes and different names. However, all of them have a ball and bearing in common. Today's topic is a joint separation in a car. At this point, we need to be familiar with the names of each joint component. Those are cap, bearing, ball and stud, housing, sealing boot, and clamp ring. Before we jump into the next slide, please remember the names of these components. If a boson becomes separated from a car while it is in motion, it can lead to steering difficulties or loss of vehicle control, making it difficult to drive and potentially causing accidents. That's why bosons are designated as safety parts in the automotive industry. Let's see what types of joint separation there are. In the automotive industry, it is generally assumed that there are 3 types of joint separation in cars. The video on the left is showing that ball stud is over travel in the operating tilting angle and is separate from housing. The middle one is a ball stud just straight pulled off from the housing. The right one is a ball stud broken by dynamic cyclic stress. In the next slide, we will have the opportunity to look at what evidence remains for the 3 failure modes respectively. This is showing the concept of how ball and stud is separate from housing due to over-travel failure. When the ball and stud is tilted and it begins to touch the housing, the leverage effect is in play. When examining parts where ball and stud is over-traveled and separate from the housing, we can see a permanent dent on the upper part of a housing, and the stud is bent, though not always. This is because the ball and stud generally has the strongest hardness among joint components. This illustrates the concept of how ball and stud is pulled straight off and separate from the housing. When examining parts where ball and stud has been pulled straight off, there is generally no dent on the upper part of the housing and no bending deformation of ball and stud. This is about how ball and stud break due to dynamic cyclic stress. When examining the general failure mode, there is no dent on the upper part of the housing and no bending deformation of ball and stud, but it is simply broken. This is a typical failure mode for dynamic cyclic stress fatigue. Now let's recap the previous failure modes. If you remember the differences among these failure modes, we may be able to tell at a glance what happened on them. The appearance sometimes gives us some idea of what type of separation has occurred on them. Now let's learn about the root causes of these separations. There are three main root causes of bolstered over travel. For bolster pull-off, there are two main root causes. When it comes to bolster breakage due to dynamic cyclic stress, there are three main root causes. Now let me talk about them in detail one by one in the next slide. This is one of the root causes of bolstered over travel, that is installing with the wrong part number. For example, a part number on the right side of vehicle is mounted on the left side, or vice versa. Installing different part numbers could cause problems in the maximum operating conditions of the suspension or steering system. That's because a permanent deformation of a stud begins to occur if it goes any further than blue zone in the middle picture. Ball joints, outer tie rod, and stabilizer link may all have different part numbers on the left and right side of vehicle. This problem mainly occurs in the stabilizer links. Therefore, please make sure if your vehicle's left and right part numbers are either different or the same before installing these parts. Here I want to talk about another root cause of bolstered over travel, that is over jounce, over rebound, over steering. The table on the left shows designed over travel torque values and the actual test results for each joint type. Stabilizer links typically have lower torque values than ball joints and outer tie rods due to the smaller ball size. Therefore, stabilizer links tend to have more problems with bolstered over travel than other joints. This is one of the root causes of bolster straight pulled-off, that is static overload. The graphs here show ball and stud pull-off requirements and the actual test results for each joint type in the global oil automaker database. For example, the graph in the top left is about the upper ball joint. X-axis on the graph represents ball sizes. Y-axis show pull-off force values. What's interesting here is that as the ball size increases, the pull-off requirements do not increase proportionally. In other words, there is no pull-off force increase in the actual car regardless of vehicle type or weight. The same goes for stabilizer link, cross-axis ball joint, and other outer tie rod. However, for inner tie rod and lower ball joint, as the vehicle becomes heavier, the stud pull-off load tends to increase proportionally. As a result, it can be predicted that stud pull-off separation due to overload is very unlikely to happen in a real vehicle. Here, I want to talk about another root cause of a bolster pull-off, that is excessive wear of a bearing inside the joint. This video shows the start of the wear durability test of the joint. The end travel curve before durability test looks linear, as you can see, and it's considered as a good part. When the wear durability test of a good part is completed, the graph may show a slight curve like this. It's still okay. However, if 40 meters of water enter inside the joint, or the vehicle is driven beyond the designed mileage, the actual end travel curve will lie horizontally in the middle part of the graph, as shown in the picture. We technically call this free play that may produce noise or vibration in the car. If this condition remains unattended for a long time, the stud will eventually be pulled off or broken. In other words, this can happen if the driver has not had a chance to notice the various symptoms of the problem. This is one of the root causes of ball stud breakage, that is dynamic overload. In the automotive industry, joint suppliers conduct a kind of a test based on the assumption that a vehicle will be subject to a high load close to its yield point 1 to 100 times over its lifetime. When a heavy load is applied, as shown in the video on the left, the part experiences repeated elastic deformation. After the test is successfully completed, the actual end travel curve on the joint may show a slight bend in the middle part of the graph. However, No screws should be loosened, and no parts should be broken. If the test fails, free play may occur, screw may loosen, or components may be broken. Here is another root cause of a ball stud broken, loose screws. If your vehicle's screw becomes loose, they will initially make noise or lose functionality, and it'll eventually cause parts to break. If a screw is tightened below the specified values, it may loosen while the vehicle is in motion. On the other hand, if a screw is tightened too strongly beyond its yield stress, it may also break. I'd like to provide a brief explanation of what happens. In general, tightening torque conditions are determined in the elastic region. However, if tightened beyond the elastic range, the screw may become permanently deformed or broken if the extra load is applied on the car in motion. That's why screws must be properly tightened according to instructions provided by the automakers. This is the last root cause of ball stud breakage, corrosion inside the joint. As previously explained regarding the excessive wear of bearing, the end travel curve should be linear at the beginning. However, if water entered the joint before or during the testing, steel component inside the joint will corrode and may produce noise or vibration in the car, like this. If this condition remains unattended for a long time, the stud eventually will be pulled off or broken. Now let's find out what preliminary signs appear before joint separation. These are preliminary signals before joint separation: noise, cylinder status, and the free play. The preliminary signs listed here are ones that drivers may recognize and notice on a regular basis. If a driver begins to hear noise from a vehicle's steering or suspension system, it must be a preliminary sign that there is a problem with the components. Here are some examples of a noise generated by joints. A squeaking noise here. In reality, this squeaking noise does not occur directly inside the joint. A slight vibration occurs at the joint first, and the vibration is amplified in the connected parts, resulting in noise. When you separate the joint from the vehicle and measure its friction torque, a good joint will look like this. But the noisy one will look like this. This spiky shape in the graph causes a vibration inside the joint, which leads to noise in connected parts. Now let's listen to another type of noise, a clunk noise from stabilizer links. This noise comes directly from inside the joint of a stabilizer link. When you separate the part from the vehicle and measure its actual end travel, good part will look like this. It's linear. However, the noisy part will look like this, a typical free play inside the joint. Let's listen to another noise that can be heard from inside the car when operating steering wheel. This is also caused by a vibration inside the joint, and the vibration amplified in the connected parts, resulting in noise. In any case, if you hear noise, this is a preliminary signal that you need to take actions. If you have a chance to take a look under the car, we might be able to gather more information. If the sealing boot fails to prevent the foreign matters from entering, the lifespan of the joint will be drastically shortened. Here I will show you the typical failure mode of a sealing boot classified in the automotive industry. punctures occur due to a hard object or tool, these impacts can often be caused by objects bouncing off the road. However, sometimes punctures are created when installing the joint in the car. If a slit or crack in the ceiling boot occurs in a horizontal direction, it is most likely due to wear. As the ball and stud in the joint move repeatedly in the tilting direction, the ceiling boot wears out due to a contact with the rubber itself or contact with the balls and housing. If the ceiling boot is torn in a complex shape like this, there is a possibility that the ceiling boot design is poor. I will show you why it is a poor design in the next slide. The videos at the top show what good ceiling boots look like when installed in the mating part. The shape of good ceiling boots appeared smooth after assembling into the mating part and seemed to contain the right amount of air. And the videos at the bottom show what bad ceiling boots look like when installed in the mating part. Do you see the difference between good parts and bad parts? The bad ceiling boots become wrinkled and distorted after being assembled with the mating part. What would happen if I drove the car with these bad parts installed? Now let me show you what happens. Car makers in the automotive industry have their own environmental simulation test requirements. As the joint moves, the atmospheric temperature fluctuates between extremely low and high temperatures, and water mixed with mud and salt is periodically sprayed onto the joint. Here is an example of environmental simulation test results conducted by an automaker in North America. Good-shaped ceiling boots appear to have no visible abnormalities until the 17-day testing is completed. However, bad-shaped ceiling boots were found torn on the second day. In other words, if the ceiling boot is in poor shape when assembled, the life expectancy decreases to less than 1/10. Last but not least, this is about free play as a preliminary sign of a joint separation. If you can leave the vehicle using some kind of equipment, you can try shaking the wheels. If you feel a gap while you are shaking the wheel from side to side or up and down, it's going to be one of two things: free play inside the joint or loose screws. If you pick up the free play joint and conduct testing in the lab, the results are as follows. If the free play is not due to the fastener loosening, a gap must be created between the ball and bearing inside the joint. There will be almost no friction torque like this graph, showing typical free end play. This free play is likely to eventually develop into noise. On the other hand, good parts still have some friction torque values, and the end trough is linear or close to linear on the graph. Now let's recap what I talked about today. There are three kinds of joint separation: over-traveled, straight pulled off, broken by dynamic cyclic stress. We could estimate the root cause based on the type of joint separation. I talked about the existence of dent marks on the upper part of a housing and the bending of a stud. We should install the joint with the correct part number. We must check whether the left and right part numbers of vehicle are different before installation. Screws must be tightened to the correct values according to the instructions. They should not be over-tightened nor under-tightened. Abnormal ceiling boot shape should be corrected. Please take immediate action if the ceiling boot shape is found to be wrinkled or distorted on the car. Joint separation could be prevented through a periodic observation by monitoring noise, ceiling boot status, free play, and so on. You can avoid the worst case scenario. This is all I have for this topic. Thank you.